In this video, we are going to take a look at electron configuration of atoms. Please read the OER textbook chapter section 4.2 for more detail. And after you finish watching this lecture video, you should start working on homework 4.2 that associate with this lecture video. Okay, so these are the homework. Please start working on this soon, so that way when you have any question, you can ask me or get help through the tutoring center or help desk before the due date of the homework. Okay, so pretty much in this video, we are going to use the idea from the previous video in terms of the rules that is have to apply in the electron configuration, and those are about principle, Pauli exclusion principle, and also Hund's rule as well. We're going to use those three to help us to write out electron configuration of an atom. Okay, so what we are going to take a look at before we get into that is we will need to relate the quantum numbers that we learn to the periodic table first, because this periodic table is really cool because it's actually arranged by the quantum number, right? So let's think about this. Okay, so this is in lecture page 55. Okay, so pretty much the quantum numbers that we learned before are the principal quantum number, okay, which is the n, right? So these are the quantum number that we learned before, which is n, l, m sub l, and m sub s, right? So which is this one would be called principal, the n would be called principal quantum number, l would be angular momentum number, m sub l would be magnetic quantum number, and m sub s would be spin quantum number. N the principal quantum number tell you about the size and the energy of the orbitals. The L tell you about the shape, what it look like, right? So for example, S would be sphere, P would be a dumbbell, and D is like a clover leaves, right? And M sub L would tell you about the orientation of each of those orbital along X, Y, and Z axis. And the number of the value of M sub L tell you about the number of orbitals that is available within that subshell. And M sub S tell you about the orientation of the electron, right, that can spin up or down, that can reside in each of those orbitals, right? So those are the value that we see earlier. So what we are going to tie this back is that I'm going to pretty much talking about the n value, l value, and m sub l, okay, because these are going to related to the orbitals itself, okay, and it's going to be related to how the periodic table is actually arranged as well. Okay, so again, the last m sub s, this is have to do with electron, whether it's spin up and spin down, that can be filled into each of these orbitals. So I'm going to pretty much focus on NL and M sub L. Okay, so the n value that we see is going to refer to the period on the periodic table. The periods are the rows, right, from left to right. So for example, the first row would be the first period, right? This would represent n equal to 1. Okay, so each of these row, the number that written here, those are indicate the number of the energy level. So that means in this case, as you increase the number of proton on an electron, right, you're going to see that it's going to get further and further away from the nucleus. You will see the energy level that for hydrogen would be only 1, right? Lithium would have 2 energy level, sodium would have 3 energy level, francium would have 7 energy level, right? Because you increasing the number of electron, you are going to end up with more layers, right, for the atomic structure. Okay, so this one right here, again, is referred as n value, which is the principal quantum number. The smaller value tell us that it's going to be smaller size. The bigger value tell us about it's going to be a bigger size. Makes sense, because as you add more layer of the energy, you are going to increase the size of an atom. Okay. Another thing I want to point out is the L value. Okay, so this is n, which is the principal quantum number. The L value would describe each of the group. Okay, so the group would be the column. Okay, so column 1, 2, right, all the way to all of these, right? So there are 18 columns. Okay, so this group right here, each of these columns right here, those are going to be expressed by the angular momentum number L. Okay, for example, the first two column. Okay, so I'm going to refer this as group. Okay, so the row would be period. the column would be groups. Okay, so group 1 and 2, these two groups are belong to S block. Okay, so this is the L value, which also include the helium as well. Okay, so the reason for that is because in this case, when L, so this is when it's described L equal to 0, which is going to be S orbital. Okay, so this is going to be S block. The reason why we call this S block, because the last electron that fill in for each of these elements, there are 2 electrons that fill into S block for that, for the outer shell of the electron. So that's why these 2 blocks are called S block. Okay, so don't forget the helium though. So there's the helium, another one right here. After S block, I'm going to, so the way that you actually write out or fill the number of electron in each of these would start from 1, because this is S block, right? So that means the first energy level would be 1s, because 1 come from the N value and S come from the fact that this is the L, right? So this is N and then S would be the L value. So that would start from 1s, right? It's come from this 1 of the N value equal to 1. Okay, so you start from 1s, followed by 2s, followed by 3s, and so on. Okay, so again, the reason why this is 7s because it's in row 7. So 7 would indicate number of N, and then S would be in the S block, right? So that's why it's going to be 7s. Before we do that, before we go to the next, let's note that helium would fill in with 1s because helium contains 2 electrons, right? So 1s contain 1 orbitals. So 1 electron can be filled for hydrogen, and for helium, you will need to fill that first before you move on to the next, right? So in this case, therefore, for helium, it have to be 1s because that 1s have to be occupied first before the next electron can be filled to other energy level. Okay. All right, so the next thing is going to be the P block. Okay, so as you see, this is the value of L right here, P block. So pretty much if you think about this, when N equal to 1, okay, so when N equal to 1, when N equal to 1, the possible value of L would be 0, and that is S orbital, right? So that's why in this case, when you have N equal to 1, you are going to have only 1s. You will not have 1p because p doesn't exist, right? Because L is restricted by only 0 in this case because N equal to 1. However, when you increase N equal to 2, you are going to have 2 more options for L. L can be either 0 or it can be 1. Okay, when L equal to 0, this is what we call S, right? So it would be 2s. And when L equal to 1, this would be P, right? So therefore, in this case, it would be 2P. So therefore, in this case, you will see that the second row right here would start from 2P, right? Because on the second row, and it's going to start from 2P, and this is belong to P block. So second row, so it would be 2P, 3P, 4P, and so on. Okay, so again, the reason why we don't call this 1P because 1P doesn't exist, right? Because when N equal to 1, L cannot be equal to 1. So therefore, in this case, this one have to be 1s, not 1p. Okay, so it's come from that. All right. So what about the middle? Okay, so now I'm going to take a look at the middle one. Okay, so the middle one, if you're looking at, is the D block. Okay, so the D block, of course, all of these going to start with D, right? Since it's D block, so this is gonna be D something. But I don't know what should be the energy level. Should it be 4, should it be 5, or should it be 6? So that's what we don't know. But what I want to recall you to is the previous diagram that we looked at earlier. Okay, so the energy diagram that we looked at earlier, according to the L, NL, and M sub L value, you will see that the D orbital start when N equal to 3. Okay, so D subshell start when N equal to 3 because when N equal to 3, there are value of L which is equal to 0, 1, and 2, right? So this would associate with S, P, and D. So in this case, therefore, the D orbital have to start from the energy level 3. Okay, so that means in this case, we cannot start at 2, we cannot start at 4, but we're gonna start at 3. Therefore, in this case, if you go back here, okay, you are going to observe that the energy level for D block or the orbital for D block is going to start from 3D, okay, and 4D, 5D, and so on. Same thing for F as well, because F is going to start from when n equal to 4, right? Because only when n equal to 4 that you are going to have the possible value of L equal to 0, 1, 2, 3. And this is S, P, D, and F. So that means the F orbital start when n equal to 4. Therefore, you are going to see that this part right here is going to start from 4F and then 5F and so on, okay? All right, so that's how the quantum numbers are related to the periodic table. We are going to use these in order to help us to fill out the electron configuration for an atom. Okay, so we are going to first use the Aufbau principle to help us. Aufbau principle state that when you fill electron, you have to fill to the lowest energy state first. How do I know which one is the lowest, which one is the highest? The order of the low energy will start from hydrogen, okay, and it's going to go to helium, okay, and it's going to go to fill into this and go this in this direction, right? So it's going to fill into this direction. It's going to fill into this direction. Okay, so that means if you know how all of these are arranged, right, you should be able to fill out the electron configuration very easily, because you know exactly like what to expect, right? So pretty much because the periodic table is arranged according to the number of increasing the number of atomic number, right? So or the number of proton. So that means when you are filling electron, you are going to fill into the same direction as well, because all of these are keep increasing. So we're gonna go from lowest energy to a higher energy level is because of that. Okay, so now how can we do that? Okay, so that's what we're gonna take a look at. So there are three types of ground state electron configuration that we're gonna take a look at. One is orbital filling diagrams. Second one is complete ground state electron configuration. The third one is condensed electron configuration. You will need to be able to differentiate all these three. And my expectation is you should be able to, you have to be able to write out this type of electron configuration as well. Okay, so there is the list of steps that I list out here, but I'm going to actually not read you through this, but I'm going to give you an example by follow this step right here. Okay, so let's take a look at an example one. So I would like to write our orbital filling diagram for arsenic. Okay, and also we're going to do complete electron configuration as well, and also condensed electron configuration. And finally, we're going to look at the valence electrons. We're going to take a look at what that means exactly. Okay, so arsenic. First, because given us the element name, so we need to actually find out first what is the arsenic chemical symbol, right? So that's what we're going to take a look at. Arsenic is the AR is not arsenic. This is argon. Okay, so arsenic would be AS. So in this case, the chemical symbol for this would be AS. Okay. The next thing that we need to look at is the number of electron. Okay, so if you go back to the number of electron, you will see that the number of electron and the number of proton are the same for neutral element. So arsenic here has 33 proton, therefore it also have to have 33 electron as well. Okay, orbital filling diagrams is going to help us to see how electrons are arranged within the orbitals. So if you remember from the previous lecture video is when you use the half arrow, spin up and spin down, right? So that would be called orbital filling diagrams. Okay, so what I'm going to do is I'm going to use this, I'm going to use this table right here that I have to help me to fill out the orbital filling diagrams. Okay, so when you are doing the practice, please try to use the periodic table that it doesn't have any label. So that's where you know exactly like what to do or how to do it, right? Without having pre-assigned the quantum number, because on the exam, this periodic table will not be given to you. It will be given to you just only blank periodic table that doesn't have any subshell label on it. Okay, so that means you have to actually get familiar with that. All right, so our destination that we are going to fill electron configuration N is going to stop right here. Okay, so arsenic 33. So that's where we are going to stop. Okay, But before we do that, let's take a look at the first step first. Okay, so the first step we have is 1s. So I'm going to have to fill electron from that in that 1s first. How many are we going to fill out in 1s? That would be 2, right? So there will be 2 electrons because 1s1 and 1s2. So that would be 2 electrons that fill into this. If you fill into this, so far you get into helium. Okay, so I'm going to go back here. I'm going to fill out electron. Okay, so in this case, I'm going to write, okay, so one, because s orbital contain only one, s subshell contain only one orbital, so this is 1s, okay, and we have 2 electrons, so I'm gonna fill 2 electrons. Remember, according to Pauli's exclusion, you cannot have 2 electrons that have the same set of quantum number. Therefore, you will need to have 2 electrons in opposite direction, one spin up, the other spin down, which is going to associate with the true value of m sub s, positive 1/2 and negative 1/2. Okay. All right, so let's go back to the next one. Okay, so now you already fill out this up to helium. Then the next energy level would be going from lithium, right? So lithium and beryllium is still in 2s. And you probably notice that 2s can fill 2 electrons because of these 2 columns. If you fill one, it would be lithium. If you fill the second one, it would be beryllium, right? So in this case, we are going to stop at beryllium 2s. Therefore, if I go back to the previous slide right here, you are going to see that, oops, sorry. Let me erase this for a second. Okay. All right, so you are going to see that we are going to go to the next energy level, which is 2s, okay? And we are going to fill 2 electrons also, okay? What about the next one? Okay, so I'm gonna go to the next one. So we already filled 2s. We are going to skip all the way to here to 2p, okay? So 2p, how many electron can fill in 2p? So you can fill 1, 2, 3, 4, 5, 6. You can fill 6 electron total. But remember, each orbital can fill 2. So if you have 6 electrons that you can fill in, therefore, in this case, the 2p should contain 3 orbitals. Okay. So if I go back here, okay, so you are going to have 2p. So 1, 2, 3. This is going to be associated with 2p that can fill 6 electrons, right? So 1, 2, 3. Remember, according to Hund's rule, you are going to fill them singly with the same parallel first before you start to pair them. So that means the next thing would be start pairing this. So total would be 6. Again, whenever that you see s orbital, you are going to have only 1 orbital. Okay, when you see p, that's when you are going to have 3 orbitals. And each of these can fill 2 electrons, right? Total would be 6, right? So again, so this dash right here would represent the number of orbitals of 1 orbital, 2 orbital, and 3 orbitals. Okay, so that's what it referred to. All right, what next then? Okay, so what next would be, okay, I already feel all the way up to here, right? Up to neon, because I feel 6 electron in 2p. The next level would be 3s, and I'm going to fill 2 of the 3s here. So that's going to stop at magnesium. Okay, so I'm going to go back here. So we see 3s, and again, s orbital contain 1, sorry, s subshell contain 1 orbital. So that means in this case, 3s subshell would contain 1 orbital, and it can contain 2 electrons that can be filled in that. Okay, so after you go to 3s, then I'm going to go all the way to here, right? So this would be 3p. Again, we're gonna fill out 6 electrons inside 3 orbitals of 3p. Okay, so in this case, we are going to do 1, 2, 3. This is 3. Oops, sorry, this is 3p. Okay, and we fill 6 electrons. So 3. Fill them singly with the same parallel first, and then start to pair them. So that would be 6. Okay, so far we are up and to argon. The next thing would be followed by this, right? So we're gonna go to the next energy level, which is 4s. Okay, so 4s would contain 2 electrons, followed by 3d. Okay, so how many electrons here? If you count from scandium all the way to zinc, you will see that it's going to contain 10 electrons. 3d have 5 orbitals. Therefore, you are going to fill each 5 orbital with 2 electrons. Total would be 10. Okay, and we are going to finish up with 4p. Okay, so 4p would contain 1, 2, 3 electron because we want to stop at arsenic. Okay, so if I'm gonna go back there. So since I'm gonna go back here, I'm going to do exactly what I mentioned to you earlier. So I'm going to start with the next level, which is 4s. Okay, can fill 2 electron, followed by 3d, and 3d contain 5 orbitals. So I'm going to do 1, 2, 3, 4, 5. So this is 3d. Okay, and then make sure that you fill in all of this. Okay, with the 10 electron in the D subshell. And then the last one that you see that we stop at arsenic would be 4p, right? I don't have space here, so I'm gonna write up here. Okay, and we are going to fill only 3 electron because if you fill more than that, it will be beyond arsenic. If you fill less than 3 electron in 4p, it would not be arsenic. Okay, so it would be 1, 2, and 3. Okay, so fill them with singly with the same parallel first. Okay, so you probably notice that, hey, wait a second, you said these are different energy level. How come that I write them in a straight, like in the same level like this? The reason for that is because I just don't have enough space. The true picture of these would be 1s would be lower in energy than 2s, 2s would be higher in energy than 3s, and 3p would be in higher energy than 3s, and so on, right? But because we don't have enough space for that, so that's why we just write them on the same level. But note that in reality, all of these do not have the same energy level. They are going to have a relative like energy level. By 1s would be the lowest, and you are going to have 4p would be the highest in energy. Okay, so that would be. All right, so the next thing that we are going to take a look at is these 4 electrons right here that are not paired. These are what we call unpaired. So when I talk about unpaired electrons, it's referred to those electrons that are not pairs, that are not in pairs. Okay, so this is unpaired electron. So again, the arrow up and down, those represent electron. Okay, so the line, right, that hold those electrons, those are what we call orbitals. And then 1s, 2s, 2p, those are called subshell that reside in the main shell. Okay. All right, so the complete electron configuration, how can we write that? Complete electron configuration is when you actually tell about the number of electrons in each subshell. You don't need to write how electron filled in. You just need to tell how many of them, right? So in this case, the complete electron configuration can be written as 1s, and then the number of electron would be indicated as superscript. Okay, so we have 2 electrons for 1s. Okay, same thing for 2s as well. It's going to be 2s, and because there are 2 electrons in 2s, so that will be superscript 2. Okay, followed by the next one, right? So we know that we already filled out the orbital diagram. We know that 2p contains 6 electrons, so it would be superscript 6, right? 3s would be 2, 3p would be 6, 4s would be 2, 3d would be 10, and then 4p would be 3. Okay, so that's how you actually filled out the complete electron configuration. Okay, so again, orbital filling, you are going to show how electrons fill in the orbitals. Complete electron configuration, you are going to actually tell how many electrons are in each subshells or in each orbitals. Okay. Condensed electron configuration is the condensed form of electron configuration. Instead of write it all listed all out like this, all of them like this, we are going to condense it so that way it's in a shorter form. And this condensed electron configuration have to rely on the noble gas that come before the element that we are interested in. Okay, so what do I mean by that? Okay, so let me go back to this real quick. Actually, let's see. Oops, sorry. Here we go. Okay, so let's take a look at this. So I'm going to, okay, so I don't have enough, so I can't erase this yet. So let's bear with me here. If you're looking at arsenic, right? So our arsenic is right here. Okay, so yellow. The noble gas that come before arsenic is argon. Okay, so that means in this case, I'm going to start with argon by using the bracket. Okay, so what I'm going to do is I'm going to oops, sorry. So let me change the color real quick. All right, so what we're gonna do is that we are going to use argon as our condensed structure, right? So the AR would be the noble gas that come before the element of interest, right? So in this case, it come before arsenic. Okay. The next thing we're gonna do is that after that noble gas, what come next? And we are going to write from there. Okay, so if you go back to the periodic table, you will see that what come next is, okay, so let me point this out real quick. If you're looking at argon, right, what come next after argon would be 4s. So therefore, it just means that we are going to start with 4s and then followed by the rest of the thing that we just did earlier. Pretty much argons tell us that it's the condensed form of the previous shell that we condense them all together in form of argon. That's what it means. Okay, so in this case, oops, sorry. In this case, what you are going to do is you are going to represent the next energy level with the 4s. Oops, sorry. So with the 4s2, right, followed by 3d10 and followed by 4p3. Okay, so again, the argon that you see here, this is pretty much the condensed form of all of these together, right, up until here. So this is the condensed form of argon. Because if you count number of electron, right? So if you count number of electron, it would equal to argons, right? So where are the number of electron? Well, it's the superscript here, right? If you add all of this together, it's going to equal to the number of argons, electron in the argons. Okay, so that's what it means. All right, now the number of valence electron. Okay, so valence electron is the outer shell electron. Okay, so the electron that is furthest from the nucleus. Okay, so okay, so how we count this is that we are going to count number of electron in the highest n value. The reason for that, we already see, right? As the n value increase, you are further away from the nucleus, right? The electron is further away from the nucleus. If you're looking at everything on this electron configuration, whether it's the orbital filling diagrams, complete electron configuration, or condensed electron configuration, you will see that the highest n value is when n equal to 4, right? When n equal to 4, in this case, the highest n value is indicated is the outer shell electron in this case. So we are going to count the number of electrons that resides in this shell. If you're looking at 4s and 4p, you will see that there are 2 and 3 electrons. Therefore, in this case, the number of valence electron that is in this atom would be coming from all the 4, the n equal to 4 add together. So it would be 2 add to 3. That would be 5 valence electron. Okay. So why is this valence electron important? So we are going to looking at chemical equations, like how atom interact, and those interaction or the chemical reaction that is undergo is going to involve with the valence electron. Okay, so that's why it's crucial. Okay, so this part right here is going to be the one that involved with the chemical reaction. Okay, so chemical reaction. It also can tell you about the group on the periodic table as well. So for example, if you have 5 valence electron, the group that is located is going to be in group 15 or in group 5A, for example. We're going to talk about those periodic table in just a few minutes here. I mean, in probably like next lecture. Okay. All right. So, oops, sorry. So I'm going to erase this so that way we have a clear picture to talk about the next step. Okay, so the next thing that I would like to do is I would like to relate the electron configuration, which explained by quantum mechanics model, to the Bohr electron shell model that we see earlier. We see in chapter 3, right, that we looking at the electron shell model by Bohr that talk about how electron is reside in specific energy level. And pretty much this is what you see, right? You have nucleus and you have like electron that orbits around, right, at a specific energy level. And when this electron transit, it have to transit from one energy level to another. It can't transit in between. It have to go completely like to another one, right? So it have to make a completely move. So the quantum mechanics model is also explained pretty much similar to it, to Bohr's model too, except each of these layers, it would contain subshell. So instead of Bohr model having n equal to 1, so Bohr model has n equal to 1 or n equal to 2 or n equal to 3. Now the quantum mechanics is actually talk about the subshell that go in each of these, right? For example, like this n equal to 1 right here would contain 1s, for example, right? This n equal to 2, right? It would contain 2s and 2p, for example. And when you have n equal to 3, right, the layer number 3, you are going to end up having 3s, 3p, and 3d, right? So that's what it tells us right here. Okay, so that's kind of like how you related to models together. The quantum mechanics just give a more accurate picture and also more accurate prediction on phenomena better than Bohr's model. Okay, so now let's get back into the valence electron real quick. So why valence electron or the outer shell electron is important and how is that going to involve with chemical reaction? The easiest analogy for this would be gobstopper. Okay, so if you ever have gobstopper, if you like suck on this, you will see that the color that changed is going to change from the outside, right? Layer by layer, layer by layer. It's not going to change from the inside right away, right? So again, if you suck on it, don't break it, right? So if you have not break it, if you just suck on it, you will see that only the outside color is changed. This is similar to an atom as well. The electron that is furthest away from the nucleus would experience less interaction from the nucleus. Therefore, in this case, the electron outside most likely to be lost or to be gained by other atom, or like by other type atom, or interact with other atom better than those electrons that are closer to the nucleus. Okay, so therefore in this case, the outer shell electron, okay, so this is the outer shell electron, would involve with the chemical reaction. Okay, and the inner shell electron, this is what we refer as core electrons. They do not involve in chemical reaction at all because they are stable. They already have a strong interaction with nucleus. They don't want to be lost or to be gained by any other element. Okay, so my expectation is you will need to know, when I talk about valence electron, you will need to know what they are. When I talk about core electrons, you will need to know what they are. Okay, so again, the one that involved with chemical reaction would be the valence electron, is the outer shell electron. Okay, so it's similar to the gobstopper, right? When the color change from the outside. Okay. This number of electrons, again, valence electron tell us about the group on the periodic table. Okay. All right, so the next thing, what we are going to do is we are going to relating this quantum mechanics into a simple Bohr electron shell model. So that way it's easier for us to see. If I convert this quantum mechanics right here and draw a picture of an atom, okay, so I would have a nucleus. Okay, so this would be nucleus. Nucleus would contain proton and neutron. And the number 1 that you see, right? So we already mentioned this, the number that come before letter tell us about the value of n, right? So this n equal to 1, for example, this n would equal to 2, for example, okay? The S, P, D, or F, those letters refer to the angular momentum number, which is the L value. Okay, so this S right here, like, is referred to L value, right? So all the letter refer to L value. When it's S, the L value equal to 0, right? So we already see this. You see this so many times now. What about the subscript? You also see this as well. All the subscript refer to number of electron, right? So this is number of electron. Okay, so this telling us about number of electron. Okay, so that means if you want to draw the Bohr electron shell model, you need to make sure that you have the n equal to 1 as the first level that close to the nucleus. How many electron that will fill into n equal to 1 then? Well, that would be 2 electrons, right? Because in 1s, there are 2 electrons. So in this case, you are going to have the first layer n equal to 1 that will have 2 electrons, which is come from 1s2. Okay. Now for the n equal to 2. Okay, so when you have n equal to 2, you probably notice that there are 2 of them, which is 2s and 2p. So these are in the same main energy level, but in different subshell, right? So that means in this case, n equal to 2, you are going to end up with 8 electron total because you are going to add the 2 electron from 2s and 6 electron from 2p. Total would be 8 electron. Okay. If you do the same thing for the next layer, which is n equal to 3, so these are n equal to 3, right? So 3s, 3p, and 3d. If you add number of electrons together, you're going to add 2 plus 6 plus 10. You are going to get 18 for n equal to 3 for arsenic. Okay. Now for n equal to 4, right? So n equal to 4, you have 4s and 4p. If you add number of electrons together, you're going to get 2 plus 3. So that means in that main energy level, there should be 5 electrons that resides in that. So again, as we mentioned earlier, right? So 5 electron outer shell, this is what we call valence electron, right? So there are 5 of them. Okay, so this is the one that is going to undergo chemical reaction. Whether it's going to lose, again, it's going to be within this layer. Okay, so again, this is pretty much how you're relating those two models together. Is give us the same picture, okay, but one is just more detail and the other is just you condense everything all together. That's what it means here. Okay, all right, my expectation is you need to be able to relate it as well between the quantum mechanics versus Bohr's model. I might ask you a certain element, right? I might ask you something else, asking you for right complete electron configuration, and I might just ask you how many electrons are in n equal to 3. You will need to be able to count that, right? So when I talk about n equal to 3, how many of them, you should be able to count that. Okay, so what I would like you to do next is I would like you to practice with calcium. Okay, so calcium is Ca, right, as the chemical symbol, and there are 20 electrons for calcium. I would like you to use the periodic table. It can be the one that pre-filled with the quantum numbers, or it can be just the blank one. I highly recommend to use the blank one, so that way it's reinforce your understanding. Okay, and I want you to start to do orbital filling diagrams, complete electron configuration, condensed electron configuration, and also tell me as well about the number of valence electron. Okay, so I'm going to give you few minutes here to complete, and when you finish, please resume the video again. Okay, so let's pause for a second, complete this, and resume the video again when you're done. All right, let's take a look at your work. Okay, so let's take a look at your work. What should be the answer for this? Okay, so if you do this correctly, follow this, right? So you are going to fill the lowest energy level first, right? All the way to calcium. So we're gonna stop right here. Your answer should be this. Okay, so let's check your answer real quick. Did you get the same or different? Okay, so it's gonna start with 1s, 2 electron, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Okay, so again, note for this. So if you're not sure, make this into your note. Note that S subshell contain 1 orbitals. Okay, and when you have P, it would be 3 orbitals. When you have D, that would be 10 orbitals. Oh, sorry, 5 orbitals can fill 10 electrons. Okay, and if you have F, it would be 1, 2, 3, 4, 5, 6, 7. It would be 7 orbitals. Okay, so those are the things that you will need to that you will need to know. Okay, so now check both as well. Okay, so both of these two complete electron configuration and also condensed, did you get the same? Okay, so check your answer. If you get different answer, that's when you will need to address your concern before the exam. Okay, so don't just wait until the exam, you will not be able to do it. All right, the last electron, you probably noticed that is going to be in 4s2. This 4 right here is in the highest n value because higher than 3 or 2 or 1, right? So that means in this case, the number of valence electron would be 2 electron, which is come from the 4s, right? So that's the 2, where is the 2 come from right there, okay? And the last electron here, you probably see that is paired. So this is what we call as paired electrons. Okay, so before with arsenic, you see that there are 3 single electron, right? So in this case, they are paired. So the other one would call unpaired. This one is called paired electron. Okay. All right. Let's take a look at next. Okay, so now we are going to relate it the number of electron. The number of quantum mechanics for the orbitals into the Bohr electron shell model. Think about this, a question that you might see on the exam. I might ask you, hey, how many electron, right, are in n equal to 3? Okay, so I might just ask you that. You will need to understand that when you are asked n equal to 3, this number that come before letter referred to as n equal to 3. So that means if you want to know how many, all you need to do is count the number of electrons, which are the superscript, right? Add them together. Therefore, in this case, there will be 8 electrons when n equal to 3 for calcium. Okay, so that's what it means here. Let's take a look at how can we write this as the Bohr electron shell model. So again, you're going to have nucleus, and then the first layer would be 2 electrons come from 1s2. The second layer would come from 2s2 and 2p6. You are going to add these two numbers together to get 8 electron total, because this is of n equal to 2, right? So n equal to 2. Okay. So now n equal to 3, as I mentioned earlier, is going to have 8 electron because this n equal to 3 right here. Okay, so it's referred to this n equal to 3. There are 8 electron total. And of course, as you already see, right, the valence electron would be 2, because in this case, only 2 electrons reside in the outer shell, right? So only 2 electrons reside in that. So that's therefore in this case, this n equal to 4 would be the outer layer, and the 2 electron would be the valence electron. Okay, so that's what it means here. All right, so the next part that I expect you to be able to do as well is that not only given the element and write out electron configuration, but you should be able to do it the other way around too. If I give you the electron configuration, will you be able to find out what is the element is corresponding to the given electron configuration, right? So for example, these two. So these two is giving you neon 3s2, 3p4. Okay, so what you need to do is that, okay, so we have to start with neon, right? So in this case, we know that we are going to start with neon, which is this one right here. Okay, so we're going to start with neon. Let me, sorry. Okay, so we're gonna start right here. Okay, and it's followed by, okay, so neon and followed by 3s2 and 3p4. Okay, so if you're looking at this, okay, so if you want to label, right, this is these two s block. Okay, this whole thing right here is p block. Okay, so sp and then d would be in the middle, and then f would be the lanthanide actinide group, right? So this would be an F. So for S, we are going to start from what? 1s, right? And then second row would be 2s, 3s, 4s, and so on, right? 5s, and so on. For P, we are going to start at 2p, right? 3p, because helium is 1s still, right? And so on. For D, we are going to start at 3d, right? For F, we are going to start at 4f. Okay, so those are the starting subshell for each of those on the periodic table. So the problem on page 57, example 3, said that we are going to have the condensed electron configuration start from neon. Okay, so that means in this case, I'm going to start right here. I'm going to start from neon. And it's going to follow by 3s2. Okay, where is 3s2? So this is 3s, right? So we have 3s2 and then followed by 3p4. So 3p1, 3p2, 3p3, 3p4. So that means in this case, your answer would be sulfur. Okay, so that's how I do this. Okay, so that means in this case, the answer would be sulfur. Let's pause the video for a second. Can you do that again on your periodic table? Figure out what should be the element for this one. What is the identity of these elements that have this electron configuration? Let's resume the video again when you finish. All right, let's take a look at your answer. So this one, if you do it correctly, it should be nickel. Okay, so that would be nickel. All right, so the next thing we are going to take a look at is the exception of the electron configuration. We're going to look at two exceptions. Okay, so one is chromium, the other is copper. Okay, so when you are writing electron configuration for chromium and copper, if you are doing this correctly, you are going to need to use the periodic table, and I'm going to go ahead, start with one. Okay, so I'm going, if you look at what we talked about earlier, using the condensed electron configuration, you are going to see that the AR is going to be the noble gas come before chromium, and it's going to follow by 4s2 and 3d and then 3d4, right? So if you do that correctly, okay. This is not a correct electron configuration for chromium. Okay, the correct electron configuration for chromium is actually AR4s1 and 3d5. Okay, why is that? Okay, so that's what we're going to take a look at. Okay, so the reason for this is because, okay, so I'm going to have this right in a little bit different way. I'm going to have argon as our inner core electron still, but for the 4s and 3d, okay, so I'm going to write this. 4s would contain 2 electrons, okay, and then d would have 5 orbitals, so 1, 2, 3, 4, 5. This is 3d that contain 4 electrons. Okay, so it's more stable because 4s and 3d energy level are very close to each other. Therefore, there is the possibility of the electron to actually go into a different energy level. So that means in this case, this 4s right here can actually jump into this one right here. Okay, so if we do this, you are going to have the result as AR, right? 4s, 1, 1, 2, 3, 4, 5, 3d, and then you are going to have 5 electron that fill in 3d. So this electron configuration right here is much more stable than what we see earlier. And this electron configuration is what we refer as the half-filled electron configuration, which is more stable than what we have previously. Okay, so this is called half-filled. Okay, which is more stable. Okay, so this is one exception that you will need to remember. Okay, so the second one is with copper. So same idea here for copper as well. If you draw the condensed electron configuration, it would be AR4s2 and 3d9. Okay, this one is not the most stable one. Okay, the correct one is actually we are going to move one electron from 4s, okay, into 3d to have the 3d to be filled with the 10 electrons. Okay, so again, if I draw this with the orbital filling diagrams, you are going to see that the argon for S2, right, is going to go into 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So that means in this case, one of these in 4s would move to the 3d, okay? In order to make it to be, it's called full fill, is make the 3d to be a filled orbitals. Okay, so that means the correct one would be AR4s 4s1, 1, 2, 3, 4, 5, 3d have to be all filled, right? Because the electron already moved from the 4s. So again, this electron configuration right here is much more stable than the above one. Okay, so this is what we refer as full filled electron configuration. Okay, which is more stable. Okay, so this is more stable. All right, so these two are the exception. You will need to know these two. It doesn't, the half field and full field doesn't apply to other element. Other elemental electron will not jump from one energy level to another, but only these two, because experimentally it's observed that the electron configuration, write them this way is much more stable than the other way that we the other way that we actually see that I cross out. Okay. All right, so my expectation for this class is that if you go back to the periodic table with me real quick. Okay, so I'm going to have to clear this. Okay, so let's go back to periodic table real quick. My expectation for you is that you will need to be able to give me the electron configuration up to element 56. Okay, so this would be my expectation right here. Okay, so all the way up to element 56. Okay, so we're gonna stop right there. Okay, so this would be the elements that can be on the exam. Okay, so it's going to be electron configuration up to element 56, which is barium. Okay, those that are involved with element 57 and above, those are going to involve with the F subshell, which is going to be more complicated. So I'm going to actually ignore those. Okay, so I'm going to stop right at element 56. Okay. All right. The next thing that we are going to take a look at so far, what we see is the electron configuration of the neutral element. The next one we're going to take a look at would be, okay, so there is the summary of these two that we just mentioned earlier about expectation of the exception of the chromium and copper. Okay. The next thing that we are going to take a look at is the electron configuration of ions. Okay, so electron configuration of ions is going to be derived from the neutral electron configuration. Okay, so the electron configuration of the neutral atom. So I'm going to start with cobalt. We are going to look at condensed electron configuration. Okay, so condensed means you need to start with the noble gas. Okay, so with this, if you go back to the periodic table, you will see that this is cobalt right here. Right, this is cobalt. Okay, and the noble gas that comes before cobalt is argon. Right, so that means in this case we are going to use argon as the starting point, and then followed by the next thing, right? So we are going to follow by this level right here. Okay, so again, this is S block. So 1s, right? 2s, 3s, 4s. So this would be 4s. And this is 3 block. It's going to start from 3D. Okay, so that means we are going to start from 1, 2, 3, 4, 5, 6, 7. So it's going to be 3D7. Okay, so that's what we're going to have here. So what I'm going to do is that I'm going to write out what I just mentioned earlier. In this case, it would be argon, okay, followed by 4s2 and then 3d7. All right. So now when a neutral atom become ions, it's going to imply that that atom lost electron, right? So if it's become 2 plus, this indicated it's lost 2 electron. Therefore, which one are we going to withdraw electron from? Is it going to go from 7 or is going to come out from the 2 from the 4s, right? So is it going to come from 4s2 or 3d7? So you have two choices here. The answer is when you are withdrawing electron, you will need to withdraw electron, remember, from the outside or outer shell first. How do you know which one is the outer shell? Okay, so we already talked about this. The outer shell electron are going to reside in the highest n value, right? So that means in this case, we know that the valence electron or the outer shell electron. So let me write this as the outer shell electron. Okay. Is going to come from the highest n value. So that means if you want to remove the electron, you need to remove the electron from the highest n value. Between 4 and 3, the highest n value is 4. Therefore, we are going to remove electron from 4s. Therefore, in this case, if you are going from cobalt 0 to cobalt 2 plus, you are going to remove electron from 4s. Therefore, the final electron configuration would be 4s superscript 0 3d7, right? Because you remove only 2 electrons, or because 4s is no longer has electron in it, therefore you can also write this as argon, okay, and then 3d7, that's also correct as well. Okay, so either you're gonna show 4s still or not showing 4s, it doesn't matter, these two are identical to me. Okay, now what happened if you have cobalt 3 plus then? Cobalt 2 plus, you already remove electron from 4s. Cobalt 3 plus, you have to remove one more from another available orbitals, right? So in this case, you are going to end up having to remove more from the 3D. So that means your 3D would end up with 3D6, or you can also write as argon, right? And then 3D6. Okay, so that means the more it becomes positive, you are going to continue losing electron, and it's going to have to go from highest n value to the lowest to, you know, like the second next highest n value, okay, and so on. All right, so I would like you to pause the video now and write condensed electron configuration for these 3 ions. Again, the best way to do this is start from the neutral element, like cobalt, like right here, okay, and then go from there, okay, because it's easier for that. Okay. All right, let's pause the video and let's do this and then come back again to check your answer with me. All right, let's take a look at nickel 3 plus. Okay, so nickel 3 plus, if you do it correctly, you are going to have to remove 2 electrons from 4s and 1 electron from 3D, right? So that means in this case, your answer should be AR 4s0 3D7, or it can be AR 3D7. It's the same thing. Okay. Another answer for rhodium 4 plus would be, oh, sorry, be KR. Where's this? Would be krypton, okay, followed by 5s0, because that's where you are going to withdraw electron from, and also withdraw electron further from 4D subshell. Okay, so the another answer would be krypton with 45. Oops. Okay, so that would be another answer. Now, what about adding electron then? Well, when you add electron, it's going to be the same deal. You are going to add to the outer shell first, which is going to be with the highest n value. So in this case, you are going to add to the highest n value. But so yeah, so we have 5s2, right? And we have 4d10, and we have 5p3. Add 3 more, it's going to become 5p6. If you look up the number of electrons here, 5p6, if you go all the way to for 5p and add 6 electrons, is actually equal to xenon, right? So that means you actually just making it to have the same electron configuration as the noble gas. Okay, so that's what it means. Okay, so again, the reason why I know it's on as xenon, because if you're looking at up, right? So 5p, if you go back to the periodic table, oh, I can't. So if you go back to the periodic table, the 5p would be, so the 5p right here, okay, would equal to, so this is 2, 3, 4, 5. So 5p would equal to xenon, right? So this is 2p, 3p, 4p, 5p, 5p, 6. So 5p, 1, 2, 3, 4, 5, 6. That is equal to xenon. So that's why our last answer for would be xenon. Okay. All right. So the next term that you are going to see is called isoelectronic species. Isoelectronic species are the species that have the same number of electrons, which is similar to the term isotope that we learned earlier, right? Iso means same. So in this case, it's the same number of electron. Iso same, electronic is electron, right? It's a species that have the same number of electron. So that means whenever that you have ions, when the atoms loses or gains electron, they are going to increase or decrease number of electron total. And somehow if those ions have the same number of electron, we call them, they are isoelectronic species, right? For example, if you're looking at chromium and cobalt 3 plus, they both, if you add all electron together, all of them together, you are going to see that the total number of electron for both of these two are the same, which is of 24. So therefore, in this case, I can conclude that cobalt neutral and cobalt 3 plus and chromium are isoelectronic species of each other. Okay, same thing for cobalt 2 plus and nickel 3 plus as well. If you add number of total electron all together, you're going to see that total of these would equal to 25, right? Cobalt 2 plus have 25 electron total. Nickel 3 plus have 25 electron total. Therefore, these two are isoelectronic species of each other. Same thing for antimony as well. When you have 3 minus, except 3 electron, that is equal to xenon that we just see earlier. So because these two have the same number of electron total, therefore they are going to be isoelectronic species of each other. Okay, so that's what the isoelectronic species mean. Okay, so if I go back to the periodic table real quick, how do I make that clearer for this? Okay, so for example, if I look at nitrogen, right? So nitrogen right now is neutral. If I add 3 electrons, okay, so right now nitrogen contains 7 electron total, right? Because it contains 7 proton here, right? So let me actually circle this a little bit better. Okay, so we have 7 proton, we have 7 electron. So if I add 3 electron for this nitrogen 3 minus would contain total of 10 electron, which is going to be the same number as neon, right? Neon also have 10 electron as well. Therefore, in this case, I can conclude that nitrogen 3 minus is going to be isoelectronic of neon. That's what it means. Okay. Same thing as well. If I looking at oxygen, okay. If I looking at oxygen 2 plus, right? So if I look at oxygen has 8 electron for the neutral atom of oxygen, but whenever that I do oxygen 2 minus, I'm going to add 2 more electron to it. So therefore oxygen would be 10 electron total. Therefore, in this case, I can say that oxygen and oxygen 2 minus and nitrogen 3 minus would have 10 electron the same, which make them to be isoelectronic species of each other. That's what it means, because they both have the same number of electrons. Okay. All right, so let's take a look at extra problem that you will see. Okay, so this would be another extra problem. Is require understanding of this whole lecture. Okay, so pretty much what is the so it's asking for the identity of the element by giving you the electron configuration, but this electron configuration is of the ions. Okay, so that means in this case, pretty much is tell you that we don't know what is element X, but this element X that contain 2 plus charge, right? That's what it means here, has the electron configuration of argon 3d3. right? That's what it means. Note that this electron configuration is already lost 2 electrons. Remember when you lost 2 electrons, where do you lost it first? From the highest n value, right? What come before 3D? Oh, you need to know that the 4s come before 3D. Therefore, in this case, the neutral element of X would contain AR 4s2 and 3d3, right? Because when you lose 2 electrons to become 2 positive charge, you are going to lose from the highest n value, which is 4s first, because if you look up on the periodic table, 4s come before 3d. So that means in this case, you are end up losing 4s first. Or on the other hand, right, this given electron configuration can be written as AR4S0, right, 3D3 that we see earlier, but it's just that it's omit the 4S0 in this case, so that's why you see only 3D3. Okay, so that means in this case, your identity of X need to include 4S2. So if you look up the periodic table, argon 4S2 3D3, you are going to see that X would equal to vanadium. Okay, so that means in this case, this is equal to vanadium. Okay, so that would be the element of X. Okay, if you do the same thing for 2 negative ions, okay, so you can do the same thing. If I choose this as Y, okay, so Y negative 2 has the electron configuration of AR 4s2 3d10 and 4p5. Note that it's already except 2 electron, right? So that means in this case, if you associate this negative 2 electron, okay, if you associate this negative 2 electron to the electron configuration, you will need to know that this negative 2 electron is already add to the highest n value orbitals. That would be 4p5. So that means it's already add into here. So that means the neutral element for Y, okay, it would be AR4s2 3d10 and then 4p3, right? Because if you add 2 more, it's going to become 4p5. And the reason why we add, because it becomes negative, right? So you add more of the number of electrons. So in this case, if you look up on the periodic table of the AR followed by 4s2 3d10 4p3, you are going to see that this is going to be arsenic. Okay, so this is the identity of the arsenic. All right, so these are an example of problem that you probably encounter on exam. Okay, so let's take a look at the review here. So pretty much this lecture chapter section is talk about how to relate the quantum numbers on the periodic table, right? So pretty much you will need to know S block, P block, D block, and also F block. Okay, and the number of and the number of each of these quantum number will go by the n value, right? So we start S from 1s. So we are going to start this from 1s. Okay, and we are going to follow that row, right, by increasing the number, the value before s, right? So this would be 2s followed by 3s and so on. Okay, so you're gonna keep adding that. Okay, for p, you are going to start from 2p. Okay, so 2p will start from the second row, so 2p, 3p, and so on. For D, you are going to start from 3D, right? So it would be 3D, 4D, and so on. Okay. For F, we are going to start with 4F, right? And then 5F. But the expectation for our lecture, our course here, you should be able to write electron configuration up until the element 56, which is barium. So pretty much everything up until here, right? So everything up until right here. So that means all of this isocycle, that would be the expectation for the exam, right? And the summary of this lecture would be, you should be able to write out electron configuration of the neutral atoms, right? And also know the exception of the chromium and copper as well. Those are the only 2 exceptions that I would like you to memorize. And you should be able to write out electron configuration for cation and also anion as well by knowing that when you are going to remove electron, is have to remove from the highest n value. And when you add electron, you have to also add to the highest n value as well, because the highest n value is indicate the outer shell electron, right? It's indicate the energy level that is furthest away from the nucleus. Okay, so that would be the summary of that. So again, after this lecture video, you should be able to start working on homework 4.2 now. If you have any question, please, again, do not hesitate to reach out to me during office hour or visit the drop-in tutor during the science help desk. And also you can schedule one-on-one tutor through the tutoring center as well. This information are already posted on Moodle.